Khandelwal. So Addy is undergraduate at our department, and actually I think he knows probably most about the labs in this department because he works in my lab, which we still talk about. In a minute, he also did his Astro 425 with Juan, so he knows about the radio lab, and he's currently taking Astro 430 with Bob, so he knows Bob's lab, I guess. But today he's going to talk about a project of a CMOS detector that is part of the Delta Seed funding, so he has been working on this for almost 2 years, and he's going to talk about some of the work he's done on this project. So let's welcome Addy.
So hi everyone, I'm Addy, and as Ting mentioned, I'm part of her instrumentation lab team. And I'll be talking today about my work characterizing high-end commercially available sCMOS detectors for optical astronomy. This work is part of like a larger collaboration of undergraduates, grad students, and postdocs as listed here, and was funded by the Dunlap Seed Funding. So to start off, a little bit about optical detectors. Optical detectors revolutionized astronomy in the 1970s by enabling us to take digital images of the night sky, which not only allowed us to quantify light sources, but also gave us larger sensitivity for a broader spectrum, and allowed us to use like computers for advanced data processing. Optical detectors turn photons into digital signals through the photovoltaic effect. So essentially, photons will hit your pixels, go to the semiconductor material, and generate these electron-hole pairs. These electrons are then collected in a potential well as charges, and these charges are read out as voltage signals, which are then amplified and digitized before turning into the digital data we see on our FIS files. And then using the digital data from a collection of pixels, we can not only look at the intensity of the light, but also the spatial distribution. And the way that these detectors amplify and digitize the charges is different in different types of detectors. So today I'll be talking about two such types. The first is the CCD, or the charge couple device, which I believe most of us in this room are already familiar with. But these detectors essentially use something called a horizontal shift register. So they actually move charges row by row and amplify them through a single amplifier. And on the other hand, we have the CMOS, or the complementary metal-oxide semiconductors, which actually have individual amplifiers and readout electronics in every pixel, which allows them to read out all of the charges simultaneously. And this readout process offers certain advantages over CCDs, such as it has lower manufacturing costs, since these can be mass-produced much easier. They have lower power consumption and higher frame rates, or faster frame rates, since they don't have to wait for the previous row to be read out. They offer lower read noise, which is something I will talk about more later. And finally, because there is no shift register, they're less susceptible to visual artifacts like blooming and smearing, and one faulty pixel will not affect the rest of the column of pixels. However, it isn't all sunshine and rainbows for CMOS. Because of this individual like pixel electronics, they're essentially a collection of individual detectors rather than one coherent detector. And what that means is there can be a lot of pixel-to-pixel variation in performance, which has historically just resulted in worse sensitivity, higher total noise, and generally a sort of non-linear correlation between the incident light and the output signal, which is why CCDs have taken front and center stage for science use. So if CCDs are so much better for science, why are we bothering characterizing CMOS for astronomy at all? Well, the short answer is we might not have much of a choice in the future. Because of their lower manufacturing costs, CMOS detectors are widely used in consumer products like our phones, security cameras, probably even the owls there. And this has resulted in manufacturers spending more resources on their research and development, to the point where major manufacturers like Sony and onsemi have actually stated that they will be stopping all production and support for CCDs within the coming year. What this means is that not only will it be harder for us to get new CCDs, but also maintaining existing CCDs will be more difficult. Luckily though, all of the research into CMOS has given rise to a new class of scientific CMOS, or sCMOS, which boasts performance and sensitivities that are on par with CCDs. But of course, we can't just take the manufacturer's word for this. We actually need to characterize them ourselves, especially in context of optical astronomy. And to characterize an entire technology, we can't just look at one detector, but rather we look at a variety of detectors from a variety of manufacturers. And we selected detectors with different pixel sizes that are better for different applications in astronomy. For the interest of time, however, I will only be focusing on the OrcaQuest today, and in particular, the standard mode of the OrcaQuest. This is an image of the detector in our lab. Also, in the interest of time, I won't really be talking much about like the detailed techniques of data acquisition and analysis, but if you're interested, you can read more about this in our paper, which we published at SPIE, or you can ask me about them later after the talk. So the first test we did is something called a mean variance plot to characterize fixed pattern noise. Now what a mean variance plot is, you have your mean signal on the x-axis and the variance in signal on your y-axis, and you essentially just fit a straight line to the curve, or to the data points, and this helps us characterize all of the different components of noise that make up the total noise in the detector. And these different types of noise can be shot noise, which is just statistical noise due to the random fluctuations in photon arrival. It is always present in every detector in a pretty known way, so that yellow line is just shot noise. Then there is the fixed pattern noise, or FPN, which is caused due to pixel by pixel variation in performance. This is something that has historically plagued CMOS, but hasn't really been present in CCDs so much since they use a single amplifier. And FPN is also more significant in the higher signal regime. And finally, there's the read noise, which again I will speak on later. But this is essentially electronic noise caused by the process of just reading out the charges stored in each pixel. And this is more prevalent on the lower signal regime. Also, when we fit the straight line through a mean variance plot, the gradient of that gives us something called the conversion gain, which I will talk about more in the next slide. So in this plot, what I have shown is the data from the median, the 5th percentile, and the 95th percentile pixels, or pixels with gain. And as you can see in the higher regime, they're all pretty much shot noise limited with barely any significant deviations from each other. And what this tells us is that this detector actually has negligible fixed pattern noise. If we did have fixed pattern noise, what we would expect is some pixels maybe going higher up, and we would have a line coming through like this. And this was something that we found to be consistent across all of the detectors we tested, which is huge because this resolves an issue that has essentially resulted in CMOS being not very useful for science for the past 50 years. Moving on to the conversion gain, this is essentially just a multiplicative factor that turns charges from units of electrons to the digital units, or the aptly named analog to digital units, or ADUs. Each histogram on this plot shows the individual gain of all of the pixels in the detector in one data set. And as you can see, I have multiple data sets plotted here, taken across several days, and they vary a lot in shape, size, and position, with about a 3.1% deviation in the median gain. And this is not good for astronomy at all, because what this means is you would need to recalibrate your detector every single time before a collection run. However, we're not yet sure if this is a result of the detector itself or something to do with our setup or any other external factors. So this is currently under investigation by an undergraduate student. Moving on, we have the linearity, which is a measure of the linear correlation between the incident photons and the output signal. We essentially want brighter astronomical objects to be proportionally brighter in our data. And historically, CMOS detectors have not really had a linear correlation for that. And while you can correct for nonlinearity computationally, it would introduce uncertainties and errors into your data. So it's better to just have a linear detector from the get-go. In the case of the Orbit Quest, we actually see greater than a 99% linearity, and this is pretty consistent across most of the detectors we tested, with only maybe one or two that were, say, 98% instead of 99, which is also pretty impressive and is on par with CCD linearity levels. Next is the read noise, which, as I mentioned earlier, is just electronic noise introduced by the process of reading charge of the pixels. So the read noise for CMOS detectors is generally lower than CCDs to begin with, and we verified this through our test. But the Orca Quest in particular had sub-electron read noise levels. And what this means is that it is able to detect individual photoelectrons and distinguish them from the background noise, and essentially act as a photon counting machine. Now this plot shows a 2D histogram of the read noise on the y-axis and the bias signal on the x-axis, which is just an electronic offshift that is subtracted away during data reduction. And this has been multiplied by a global average gain value. And while this might look okay to you, watch what happens when, instead of using a single value, I multiply each pixel by their individual gain. Now, the noise properties are completely different. Fortunately, this doesn't seem to affect the read noise so much. And in this case, the bias signal is getting subtracted away, so it doesn't really matter. But it does highlight just how important it is to consider that per pixel performance when using CMOS instead of just global average as you would with the CCD. Next we have dark current, which is signal generated by the thermal excitation of electrons rather than incident photons. And these have historically been higher in CMOS than CCDs, and our tests have shown that while the current generation of sCMOS do have very low dark current values, they're still nowhere near CCD level by like at least an order or two of magnitude. This is the plot for the dark current distribution of the Orca Quest, and while it may seem like a very large spread, all of the pixels that are greater than 0.1 electrons per second make up less than 1% of the total pixel count, so this is actually fine. And notably, the Orca Quest is the only CMOS we had that had dark current levels that were not just on par with, but in some cases better than CCDs, with 0.0067 electrons per second. But this isn't generally true. This is not generally true for the other sCMOS detectors. The final test we did was quantum efficiency, or QE, and this is essentially a ratio of how well the detector is able to turn the incident photons to signal at every wavelength. Unfortunately, we didn't really have time to test this like in detail, so we were only able to collect a global data for the Orca Quest, and we weren't able to really test any of the other detectors or any of the other modes or do a pixel-wise analysis. So this is definitely something that we still want to investigate more. But we see that the Orca Quest had an 82% peak efficiency, which is lower than CCDs, but this matches like very well with the Bender curve. The other sCMOS detectors, on the other hand, did report having peak efficiencies up to and above 95%, which is around the level that the CCDs are as well. So the main takeaway from our work is that sCMOS technology now has not only caught up with CCDs, but in some aspects it also surpasses CCD performance, especially for optical astronomy. So modern CMOS detectors have negligible FPN and have much lower read noise than CCDs, but they also have comparable levels of linearity and quantum efficiency. And while they do still have much higher dark current than CCDs, their dark current is very low. some of the future work that we want to do for this project is install our detector on the half-meter telescope at the Car Observatory and collect some on-site data. Do further investigations of the variation and conversion gain and the quantum efficiency testing, and finally add to our roster of detectors that we've characterized. Thank you.
So we have plenty of time for questions. Anyone want to start? Yes, go.
In the QE curve, there's like a bit of an uptick in the UV. Do you think that's reliable?
So this QE curve actually has been cut off at 300. It used to go further. We realized that there were some issues with the QE bench, but we do think that it is reliable up to 300 nanometers. Anything past that, we kind of cut out because we weren't really sure. But this is also present in the vendor curve, so yeah, we think it is reliable.
Any other questions? Yes.
When you mentioned the fixed pattern noise, is that before or after correcting for gain differences between pixels?
This is after correcting for gain differences.
Because at some level, when I think of fixed pattern noise, that sort of gain variation is different by pixels. So you've measured it, but you basically, so this tells you can really take it out really well and still be nicely linear.
Yeah.
Okay.
So all of the plots that I've shown here have units of electrons instead of ADUs.
Right.
So everything has been like corrected using the gain to give like raw units.
For each pixel, and that's
Yeah.
really the main difference, right? You have to correct for it. Okay. Thanks.
On this graph, it looks like it stops around like 1,000-ish. Is there a reason why this kind of is cut off that you don't test below that serial? Or then
Right. So the reason for this is because I was using a linear scale time division from 0.001 seconds to like 5 seconds, and I didn't realize at the time that that just meant a linear scale meant all of the exposure times that would give this data is just not there. But it doesn't really impact our findings because, as I mentioned, fixed pattern noise is more significant in the higher signal regime, which we have enough data to properly characterize. It would be nice to have data in the middle regime, but generally the mean variance plot is just fitted to the shot noise in that region anyways, so I don't think it would give us any more insights. And as for the lower regime, the read noise for this detector is actually below the axes of the plot. So again, it doesn't really make any difference here.
Thanks for the really interesting talk. So it seems like the detector that you were talking about today performed better than some of the other detectors that you work on, and just there's been a general improvement in CMOS detectors. So I was wondering, is there a sense of like what is actually leading to that improvement? Or what makes this detector better than the other ones at these various tests?
Yeah, here I actually have the results, like all of the results from all of the detectors here. So essentially this detector is like advertised as being a quantitative CMOS instead of a scientific CMOS, which is just a term that the company coined themselves, so I don't know if it's like an actual thing. But like they made this to be a photon counting machine. So they specifically designed it to have like super low read noise levels. I should also mention that none of these detectors are actually meant for astronomy. They're just like general scientific CMOS detectors that we want to test for astronomy. Does that answer your question?
Yeah, thanks.
So I'm used to detectors that do photon numbers out them that are really cold, but it seems like the Orca Quest 2 isn't acts in room temperature. So do you think using CMOS technology that is designed for very cold measurements, there's not that much thermal noise would be useful enough?
That's a great question, and that's actually something that I forgot to mention. So these detectors don't actually work at room temperature, but rather they're cooled to like -20 degrees. But this is just air cooling, so we're not like pumping any nitrogen or helium into them. This is just the internal mechanisms of the detector are able to cool the chip down to this temperature.
Okay, any more questions for Addy? You want to have more question? So, okay, one more, last one from Peter.
Truth in advertising. Overall, what did you find about the manufacturer's claims versus your actual measurements?
They were generally true. In some cases, our measurements outperformed theirs, and in some cases, they underperformed. But like, if I were to take a step back and like make a general claim, they were pretty much reliable.
Follow up, through SPIE or other contacts, there must be other labs doing measurements like this. So, are you learning from those measurements? Are they learning from you?
Yeah. So one of the papers that I heavily based my work on was another such team that was doing sCMOS characterization, but they were using like lower cost CMOS versus us using like higher cost CMOS, which are I guess like 5-digit price points. So yeah, a lot of the results, a lot of the graphs that I have are inspired by the way that they made their graphs, just so I could compare what our results look like versus theirs. And most notably, the difference comes in like here, because as I said, we don't really see fixed pattern noise, but the detectors that they characterized did have like a fixed pattern noise line going through it.
So it's worth paying more money.
Yeah.
Get what you paid for.
Okay, great. I think Addy has answered a lot of questions, so I'll stop here for Addy. Thanks again.